bending. The first topic that we will be doing is bending, as I have told you in my previous classes as well, and it is a very important topic, especially from the examination point of view, because here we will be doing the real world bending. That is means after studying a basic intro of bending, we will be moving on to combined bending and axial loading, eccentric loading, and then finally we'll be shifting to axisymmetric loading or asymmetric loading. So, so this is an example of a beam in which, if you look at it, these two arrows, purple arrows, are telling us about the movement. And then if you look at it, this picture, this is a beam, okay, and it's basically some length, width, and it has got depth. It is smaller compared to the other segments. So if you look at this thing very well, that these things over here, if you look at it, this and this, the greenish stage and the blue stage are basically showing us the stresses. Okay, and since these stress, there is as a result of this movement, the stresses are being generated, and as a result of vertical transfer forces, there will be shear forces generated and shear stresses will be generated, and as a result of this movement there will be stresses generated. Because the stresses are generated as a result of movement, and bending is being basically as a deformation loading mechanism here, so these will be termed as the bending stresses. So if you look at this picture, okay, so what I have done is I've taken different pictures and I've tried to put it over here in this frame. And if you look at it here, this is a rectangular beam. So one of the assumptions that we will be considering here is that this beam, which is over here, is basically made up of fibers. We assume that the beam is made up of fibers, and you can see those fibers are running along the length of this beam. So one of the assumptions is this. So when the deformations occurs as a result of bending, as a result of shear forces, it is clearly conspicuous to see where are the main deformations been happening. Okay, so this is like the before deformation scenario, and it is undergoing plane symmetric bending. Okay, and as a result of it, the bending is about the z-axis. If you look at it very clearly, and you can see that these are the horizontal lines over here. Okay, becomes curved because of the bending. Here they were straight lines, and the vertical lines remain straight at one area, which is called as the neutral axis. Because at the neutral axis, when the bending stresses have been generated, it is a very unique plane on which we will see that there will be no stresses being generated, bending stresses. Okay, like this. If you, this is basically a beam on which again these bending moments being applied, and the bending stresses are being generated, and this is the stress profile of the bending stress. But as I told you, along with that, if loading is being applied on a beam vertical, there are concentrated forces, or as a result of some UDL is being generated or a VDL is being applied on a beam, there will also be some sort of a shear stress is generated. This is the profile for a shear stress of a rectangular beam. These profiles, the bending stresses and the shear stress profiles, will actually be a function of the cross section of the beam. Okay, so if you have about a Z section beam, a channel beam, an L section beam, a T section beam, or if you got a the I section beam, as you can see in here, the bending stresses profile will be different because it will be depending upon the material, it will also depend on the loading, and also hugely dependent upon the specific cross section as well. Okay, so what we are always interested, as I've told you here, is that the deflection configuration is very important. Okay, that because of this movement, what is going to be the deflection about the neutral axis, and we are interested that this deflection should stay within the elastic limits, and we do not go into a yielding zone. Otherwise, it might result in a failure. So again, this is showing you the configuration of types of loads that can act on the beam. Definitely on the top, you can say movement is basically a load. Then again, if you look, if they have given you an example of a cantilever beam. And if you look at this cantilever beam closely, it is being fixed to the wall here. So it is basically what we can assume is that it is a fixed support. We can assume again any type of cross section. You can have a circular solid rod. You can have a solid hollow section of a tube-like structure. You can have a rectangular cross section or any cross section depending upon the design and the type of location where this beam is being applied in the industry or basically at any loading place depending upon the load. Okay, so this is the finite analysis of a beam. Okay, this is an I section beam. How the bending stresses are being generated in that beam. Okay, and since again it is a complete replica of this thing over here, even though they're showing us the cross sections of rectangular and circular cross section, but here it's a unique cross section which is the I section. And then again, one of the reasons that you must pay attention is that why are we studying bending? The point is that why did we study bending in solid mechanics 1 second year, and why are we studying again bending in third year also? The reason this pictures tells you a very heartbreaking picture in which you can see a very bridge. And if you look at this bridge has basically catastrophically failed as a result of the loading. Then again, if you look at the pictures and you can see the black circles in this bridge, if you look at it very precisely, you will see that in this bridge, if you look at it, this circular area is showing a failure. Okay, you can see again this is a typical example of an RCC bridge. Okay, reinforced concrete bridge. Why you can say this? Because if you look at it, there is iron rods, twisted iron rods passing through the concrete. Okay, and if you look at this section of this beam, okay, if you look at this section of the beam, this is then showing us a shear failure and this is showing us a bending failure. And if you look at it, why this is very important? Because a bending failure in any of the beams, a bending failure in any of the beams will be generated as a result of what? Yes, it will be generated as a result of this stress. This stress is the bending stress. Okay, so this is a failure. And what about this? What about this failure? Shear failure, you can see it's acting at some angle of 45 degrees approximately. It's not going to be exactly 45, say 40 or 41, 47, 48 degrees, somewhere at 45. Along, if I make this column vertically straight. So you can assume that it will be approximately 45. So this failure, if you look at it in a beam, you can instantly say that it's a shear failure. So why shear failure is very important to us? Because a shear failure will be generated will be generated as a result of the shear stresses exceeding certain threshold limits of the limit of that the strength limit of that shear strength limit of that beam. Okay, and why it is being produced here? Because of these forces. It can be a point force, a concentrated force, it can be a distributed force, it can be a surface force that can result a shear failure. And why it is important? It is important because of this stress. If you look at it, this stress is called as the shear stress. It is called as the shear stress. And a shear stress for a beam with a rectangular section, with a beam with a rectangular section or with a beam with a square section will have a shear stress profile something like this. You must just see these pictures in your this presentation. In depth we'll go afterwards. Just so what does these pictures explain? A bridge has failed, and one of the reasons of the failure of the bridge can be a bending failure. Another reason of the failure of the bridge can be a shear failure, and sometimes it can fail as a result of Mother Nature's excessive forces, and it can result both of those failures, which is the bending failure and the shear failure. Sometimes it can fail as a result of the column failure. Okay, the column undergoing shear deflection. Okay, and it can fail as the column can fail itself. There will be no bending and shear, but the column will fail as a result of deflection. Okay. Then if you look at this picture over here, we will start with the bending. Okay, so structural loads is talking about load means it's a very important term. We will be using this term a lot in our theory structures. Means it means forces and moments. So whenever we say loads acting on a structure, you instantly what must come into your mind? It must be the moments applied to the structure. Okay, or it can be the forces. Forces and moments both can be applied to any structure and they can be contributed as load. Okay, they can be either be externally on the surface as surface loads or developed within the surface like the body loads, which can be the gravitational loads. Okay, for acting through and loads are further considered. Again, loads can also be differentiated on the basis of whether they are static, which means the force that you applied is not a function of time, and either sometimes the loads can be dynamic. It means that the force which is applied is not static, but it's a function of time. There is some frequency and amplitude in that force applied. Okay, it depends further that whether it's a uniform, it's a steady state loads, but it's not uniform. There is some sort of decay, there is some sort of variation in the loading and in the frequency and amplitude of that force vector. It means that those loads are basically not steady state, but they are transient. Okay, so just for the knowledge point of view, they are of constant magnitude, direction, and location. Although structures, for example, a civil structure, again, building, you will always treat it as a static because it is static. There you can not see any changes in that, in deformation, something like that. But again, remember in my previous lecture, I have given you information and knowledge about the live loads. You can have twister, you can have basically a tsunami, you can have an earthquake. So those loads also you have to incorporate into your design. Okay. So, but again, such are loads in which there is time is changing very. The loads are very slow in change. It can be creep loads as well. So they are termed as basically, if you look at it, you will call them as if you look at it, you will call them as quasi-static loads. Okay, so this is very important, and it means that the initial forces due to acceleration may be neglected with respect to difference of externally applied force and initial twisted force. So dynamic loads itself uh, are loads that maintain the same character frequency, that is over the long term, which means that the frequency and the amplitude. Okay, the frequency unit is number of cycles which are acting per second. It's not changing, and the amplitude by means I mean the crest and the trough magnitude remains the same. Okay, over the long term. But transient loads are changing loads. Okay, which means that they can either decay or they can basically what is going to basically they can expand with time. So which means they will not be uniform. Okay, the load and the frequency and the amplitude will not be uniform. Load will be a function of time. So here is basically the loading, simple load orientations. Okay, single-headed arrows and forces, double-headed arrows are movement. So this is one of the assumptions. Remember, if there is a single force as a load acting over here, single force as a load acting over here, these are loads. Like this, if you look at it, these are two forces, which is a load, which is a force. But if you look at here in the banding and the torsion, there is not a single arrow, but there are two double arrows. So if these two double arrows are showing you, this means that they are moments. So this is one of the assumptions that we use in statics a lot. Okay. Then we go to another very important. Common structural loads are summarized as the structural loads can be summarized as the surface loads and the body loads. So the structural loads, remember, can be two categories: surface loads and the body loads. We will be encountering a lot. 99% you can say will be acting in our solid analysis 2 as the surface loads. Okay. They can basically be categorized as concentrated force as the point load. Okay, and you know the unit of the force is basically Newton or pounds, and I can have a distributed force. So by distributed force, what comes to your mind? They say Newton per meter, or they say pounds per inch. So what does that mean? It means that what does it means? That it's basically a loading. A loading means UDL. It's basically a UDL and pounds per inch. And if you look at it below, it can also be a line load. A line load acting on a structure is basically not a loading, but you can treat it as a pressure. But if you tell you, you have to be very much like this Newton millimeter is from solid mechanics one. It's mega. But this pressure will be not omega because you have to look at the units. If it's Newton per meter square, that line load is pressure. Otherwise, it's Newton per meter, you treat it as distributed force. Then you go for the moment of the couple. Okay, the moment of the couple is the bending moment or the torsion moment. So it will be Newton meter. You know the unit for movement or a couple, it will always be Newton meter or the pound inch. You can also call it as the bending moment. And sometimes if you are doing shaft analysis and there is a moment generated in a shaft, so we will, instead of calling it bending moment, be and there is a torque being applied on that shaft structure as well. So we can treat it as a torsion moment. Then you have the body loads. The body loads is the gravity, again the surface loads that I told you we'll be dealing with. Then there is another loads which is the body loads. They are always treated as the gravitational force. The gravitational force, remember, the unit is same, Newton and pounds, but it is the gravity load or the weight, which is W equals to mg. But again, the body loads can also be treated as thermal stress. If there are, even though no structural loads and temperature variations within the beam, uh, then there will still be stresses generated into the beam, and that will be termed as the thermal loads. And the result of those thermal loads over some suspected cross section will be the thermal stress. Then we go to the units again, just like remember the pressure, the units per Newton per meter square are psi. The same with the thermal stress, the units will be Newton per meter square or the psi. Then again, taxonomy of the structure. If you look at it, whatever taxonomy structure is basically, if you have a complex structure, one of the techniques is basically you cannot solve the complete complex structure into a single load, like an fuselage of an aeroplane, or complete structural analysis or vibrational analysis of a fuselage of an aeroplane. You have to break it down into its subcomponents. Okay, so this knowledge will attempt here a taxonomy on the basis of this. What we can assume is that work well for simple linear assumptions. But if you have got some non-linear aspects of analysis incorporated in your system, it will not work well. But for our case, it's very simple, and we will have a taxonomy classification of structures, which is by decomposing them into structural elements, simpler parts. Okay, and so for linear techniques we're talking about here. So the real structures are comprised of different types of elements and may assume a very different rules. Okay, so carrying load, the prime function structure is largely determines the form of the structural elements. Load carries its loads by the structure will be again the loads I told you: tensile load, the compressive loads, the axial loads, the shear loads, the torsional loads, the bending moment loads, then distributed loads. But these are again the what we are talking about, and then there will be body loads, the gravity loads, the thermal loads are the body loads, and then the surface loads that we have discussed it before. Okay, so now he's talking about structural form falls into two categories: the line forming and the surface forming. So the surface forming is further subdivided into area forming and volume forming elements. Okay, so here it is, you have for line forming elements and surface forming. Okay, so we will be dealing a lot with basically line in our SM2, but there are all, when you go in advanced studies in your next year for stress analysis, you will be incorporating the surface forming elements as well. Okay, so you need to have a knowledge of line forming elements and the surface forming elements. Okay, so the line forming elements are slender structures. What are the actually what comes to your mind? What are line forming elements? These are the slender structures which give one spatial dimensions, which means all length is their main basically spatial dimension along a specific axis. Okay, and significantly we can treat it approximate in our books, we take it as an x-axis. greater than any other dimensions, which means the width and the height of the width, height, and thickness. Line elements may be represented as lines, either straight, again straight भी हो सकते हैं, they can be curved as required. Remember, we have straight beams a lot in the studies, but we have also special type of beams which are curved in nature. I've shown you by some pictures also. A curved beam. If you basically go on a bridge which has a curvature, okay, like if you go from uh, so the Safari Park bridge of ours, if you look at it, that bridge is not a straight bridge. You make a curve and you go to the Safari Park road of Nipa, towards Nipa. So it's a curvy bridge. So you can have straight elements, but you can have straight linear elements, and you can have curvy elements and curvy. Then again, if you look for a curvy element of a line element, we talk about it's a crane hook. Or if you look at your roof, your fan is basically being also attached to a curvy structure. Okay, it's a curvy beam. Okay, so line forming elements can carry loads in tension and compression, torsion, bending, and some combination, which is studied in the next. It's called combined bending and axial loading. It can be combined bending scenario. You can have a tensile load and you can have a movement. Okay, you can have a shear load and you can have a compressive load, or you can have a bending load, a shear load, a loading, and a movement. So they becomes combined loading scenarios. They are complex loading analysis. Inshallah, we will study as the course will proceed. Okay. So line forming elements may form axial, torsional, or bending structures such as rods, cables, and beams. Okay. So if you look at this thing, a taxonomy of structural elements, if you look at it very well, you have got a line forming elements and you've got structural forming elements. Now you'll be looking. I already told you line forming elements will be the cables, the rods. You have already done in your axial scenarios in your second year, and beams also a little bit you have done in your first second year also, and now we'll be discussing a lot uh, in the third year SM2 also. So it is characterized for tensile axial. Tensile means axial loads for the cables. They will always under tensile. I have told you in my previous class, the rods, the beams, they can also be characterized line forming elements. Certain cables do not undergo compression, they will always go under the axial category. But the rods can have the tensile and compressive behavior. What about the beam? Beam can have basically a tensile, axial, and compressive scenario as well. Okay, or it can also undergo direct shear. No, the cable cannot go, the rod cannot go, but the beam. Again, this is very important configuration when you're doing beam design. Or basically, if you work in companies like Descom of Pakistan, if you go abroad to Saudi Arabia and you are in the structural element, are basically in some sort of a consultancy, design consultancy, you need to have the knowledge of this thing when you're basically designing any structure. Okay, the torsion movements, if you look at it, you have the cables uh, will not be going any torsion movement, but the rods can undergo torsion. It. Even the beams can undergo torsion as well, because if they can undergo movement, they can also undergo a torsion. The bending movements, only the beams have. No, the cable and the rods do not have any bending movement scenario. What about the distributed force? Yes, the cables have excellent distributed capabilities. Rods do not. You can never see a rod undergoing a distributed load, but beams, yes, they have got UDLs and they have got VDLs. And the thermal scenarios, just because the cables are reinforced with steel structures embedded into them, they can undergo thermal variations. The thermal stresses could be generated. Same with the rods, depending on the material. If it's basically a conducting material, it's got high conductivity, thermal stresses will be lot. If we have concrete structures, then again slightly the thermal stress magnitude will be less, and the beam can undergo, because there are RC beams and it's a metallic bridge. The thermal stress element is still going to be incorporated. And then we go to the complex mode. The surface forming, area forming is basically the plane membranes and the curved membranes. Okay, so plane membranes, it's telling you about if you got a plate. Okay, plane membrane will undergo tensile axial, plates will undergo tensile axial for the area forming, and they will not undergo compressive axial, but they undergo basically the plates will undergo. Okay, and You can see all these things. The curve for the curved membranes will undergo tensile axial, and the shells will also undergo the tensile axial. And you can take all these scenarios. Of course, we will not be studying them, but you need to have a little bit knowledge just in your brain. That there are plate membranes, there are plates, there are curved membranes, and there are shells. And if you want to further see, you remember my second, first presentation, I've shown you the pictures of these curved membranes, these plates, these shells, everything. Okay. Okay, a little bit undergoing to the mechanics of these structures. Very important for you to understand the mechanics. Like rods, if you look at it, these rods, they will all. If you look at the previous uh, uh, the rod will have basically a response under tensile. Okay, that rod will have a response tensile. It can also have a response under compressive. It can have a torsion movement, and it can have a thermal response. So this is a very beautiful taxonomy of structural elements. I really like it, and it will, if you look at this and learn it, it will tremendously increase your knowledge of structural elements. Okay, so let's study this a little bit because this is very important. And so rods are carry concentrated axial forces in either tension or compression. They Thus they are axial structures or pin boundary conditions are requested. Okay, so which means just trying to telling you about the taxonomy of the rods, about the axial and basically compression natures, and the cross section batteries can take any shape. Circular भी हो सकती है, rectangular भी हो सकती है, और क्रॉस सेक्शन अगेन क्योंकि रॉड है, इट कैन बी सॉलिड ऑल्सो, इट कैन बी hollow. केबल्स की क्या बात करता है? They carry concentrated axial tensile force but not compressive. You cannot push a rope. Again, that's very logical. अगर आपको rope हो तो आप rope को कोशिश करें push करने की. No one in this world can do that because it has a tensile response. So it's concentrated distributed transfer forces X. Okay. So the cable deforms under action of transfer load in such a way that remains axial structure. ये आपने फर्स्ट ईयर के अंदर इंजीनियरिंग मैकेनिक्स स्टैटिक्स में केबल्स आप लोग पढ़कर आए हैं, तो डेफिनेटली इसकी मैकेनिक्स का आपको पूरा आइडिया होगा. तो एज विद रॉड्स ओनली पेंट बाउंड्री कंडीशंस आर रिक्वायर्ड. रॉड्स की जब बात करते हैं तो पेंट होती हैं, तो क्रॉस सेक्शन ज्योमेट्रीज मे बी ऑफ एनी शेप, बट सर्कुलर क्रॉस सेक्शंस आर कॉमन. बीम्स द मोस्ट इम्पोर्टेंट बीम्स हम करेंगे. अब अगेन वो खुद बात कर रहा है, कह रहे दे आर द बीम्स कहाँ आ रहे हैं आपके पास? दीज आर द बीम्स. दे आर द मोस्ट कंप्लीट line forming elements since they can carry axial. अगर आप पीछे वाली पिक्चर पे जाएं हमारी टैक्सोनॉमी की और बीम को देखें, तो ये देखें सारे टिक लगे हुए हैं, टिक 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 टिक, all ticks. Why? This is showing the importance of beams in mechanical engineering, the importance of beams in structural engineering, the importance of beams in architectural engineering, why beams are so important, and again I will add the importance of beams in automotive engineering. I will again add to importance of beam in aerospace engineering, importance of beam in basically aeronautical engineering. Beams are the most important structure, and this taxonomy will clearly show the importance of beam, why beams are so important. Okay, let's go ahead and see what this says. Okay, they can carry axial, compressive, tensile, as in rods or cables, as well transverse, concentrated and distributed forces and cable. Moreover, they can carry the torsional loads and the bending moment loads. In cases where movements are applied, as at least one boundary conditions must be able to support the movement reactions. For example, fixed or built-in conditions. Cross-section shapes may be of any geometry, solid or hollow. Okay, so they are telling you about the nature of the beams. You can have any cross sections. I've told you in my previous slide, week 2 videos, you've seen H section beam, I section beams. You can have circular beams, you can have solid beams, and depending upon the types of loading and the location, and depending upon the weight parameters of the structure, you can have hollow beams as well. So depending upon the place and location where the beams will be basically installed in your structural. So this is the cable, this is the FBD for a rod, this is the beams. So So pictorial symbol. This is again a plate membrane. This is a plate. This is a plain membrane, and this is a plate. Okay, this is membrane. This is plate. Plate is 3D. This is 2D. This is a curved membrane. Okay, and this is your shell elements. Okay, yeah, okay, shell elements and schematics of basic structural elements. You being engineers, you must able to differentiate how a plate is being schematically shown, how a curved membrane, how a shell is being schematically shown. So this is very important for solid mechanics and when you do bending, and especially advanced bending aspects we'll be covering over here. So this is the part A. This is the part A of this presentation. I will basically start the second presentation as part B. Okay, so I will try to make it out in 2 or 3 different segments for you guys to, so that it could be easily understood. So I will be making another presentation for this. After that, it will be part B for the bending. Okay.